Good, so it's about Brownian motion equation spatial PDEs.
Thank you. Before starting my talk, let me take the opportunity to thank the organizers for inviting me and giving me a chance to present some of my recent research and also some remarks to the talk. This is the idea is to give an overview. So we are looking for a solution to a spatial PDE problem, and I will present to you what is state of the art, and then I'd like to present our approach, which is based on Brownian motions for SDEs. There's quite a lot on the agenda, so I try to keep the presentation very simple, so there are no results in full generality. This is also work in progress, so we say we are at an early stage of this project, so I would be happy to hear about your opinion about what I'm going to present. And one aim of this topic is to combine expertise in analysis and stochastic, something which is highly recommended at our institute, and that's one of the reasons why there are so many courses. Okay, quick overview. So I'll give you a problem formulation in a PDE setting and tell you something about Fermat-Katz formula, which somehow links the two approaches I'm going to present. PDE problem, state of the art to solve this is finite element method. Give a short reminder, short overview for those who know about it, and yeah, for those who are not familiar with it, kind of short idea of what is done in such a finite element method. As my title already said, we will be looking at extend this problem to stochastic coefficients, and the last point I will talk about our approach for the problem. Yeah, so we will deal with some boundary valuing problems for there's something missing for partial differential equations. I'm going to present two numerical methods. So our solutions will be numerically given. The first is, as I already said, the finite element method. The second is an SDE approach, and applications. There are many applications, for example, electromagnetism, heat transfer, and fluid dynamics. Problem we are looking at here, partial differential equation is given. We define this right-hand side as some kind of operator capital G, and we also have an initial value problem given, so at time 0 the solution will be given by a function of x, and use simply maps from some time interval 0 capital T times r to r. And for that problem, as I already said, we are looking at the Fermat-Katz formula. Given such a PDA and a PDE and some coefficients mu and sigma and function f, our solution U can be represented as a conditional expectation. Conditional expectation given with some measure P of our initial condition function f. We are looking at some SDE solution capital X starting in the point small x. We're looking for this SDE as a capital time T, and the solution in small t will be given as a conditional expectation. As I said, this is the SDE following having some drift coefficient mu and some diffusion coefficient sigma.
What is the definition of capital T?
Of capital T? Just some fixed time interval.
I think you
look at the solution at time t.
I think there's a typo because somehow you turned it around, right? I think you should look at the solution at time little t. If you start out from the PD that you considered in the last slide, if I didn't make a mistake. Yeah.
So, also given as an initial value and not an...
Yes.
Nevertheless, the measure P is given such that we use Brownian motion under that measure. Okay, some application. We're looking at Darcy's law. Darcy's law mainly describes flow of some fluids through porous media. It's given by that differential equation. So U is given as some physical constants and pressure gradient. So U is a flux, as I said, T is a pressure gradient, and these physical constants are permeability and viscosity. And looking at this equation, you have two unknowns, but together with a conservation of mass, so the divergence of U is some function f. We get an elliptic equation. And with some boundary condition not specified yet. And for such an elliptic equation, here, just to give you an idea, we have some example. It's a finite element solution to the problem Laplace U is 0, and the boundary condition, some deviatory condition, is given by sinus px, and we are looking at the problem at unit square, and what you may keep in mind, because we come back to this later, is this cross, significant cross, which is given in this orange, slightly red color. As I already said, we are talking about elliptic PDEs, so it's a second order PDE, and elliptic PDEs are some stable state of evolution problems. So they are obtained as a limit of time, and therefore they are independent of time. And we define such an operator, capital G, acting on some process. So X will be this time from space Rn, and we have drift coefficient mu, and somehow diffusion coefficient sigma, which will be given as such a matrix. U this time is mapped from a domain D to R, and outside of this domain, or at the boundary of the domain, we are given some condition Ux is f on x, and in this case this is a diminishing condition. For such a PDE, we can once again state Feynman cuts. This time, somehow we have this boundary condition f, as it already was in the previous Feynman cuts theorem, and this is attained if you stop. So tau is the stopping time defined here. This is just the first time you leave your domain, so you are the complement of your domain, and if you are not stopped, so what you else you have to account for is some time, some integral over 0 tau, so the time you are going until you stop. This is valued by this g of x.
You consider vector case, yes?
Yeah.
X is vector.
Some words about finite element method. So we are starting with some PDE, with some operator capital GU, and this is equal to G. And what we are then going to do is provide this in a weak formulation, in some variational form, and we define some additional operators G tilde, which is just the inner product of capital G of U and some test function V, and we define small g tilde, which is the inner product of the right hand side function G and test function V, and somehow these weak formulations give rise to additional mathematical tools. And when we are in this weak formulation, we are looking at some finite dimensional subspace UH, and on these finite dimensional subspaces it's easier to solve our problem. So we are looking for a solution UH coming from this subspace, that solves our problem capital G tilde equal to G tilde. Also follow test functions, but these test functions are only on the subspace. And if you consider the basis of such a subspace EI, then you can represent the test functions V as a sum of some weighted basis. And if you plug in, then you can pull out the coefficients, and this is an equivalent to equality on the basis functions. Some more words on the finite element method. It solves the algorithm globally, so that is one main feature, that you have a global solution, as you already saw in the picture. As is state of the art and highly used, there's also a very good implementation of the FEM algorithm. So they use vectorization, parallelization, and many things more. And yeah, this is something one have to keep in mind when you try to compete with another approach. So our approach will be, as it is right now, based on some straightforward implementation, so you definitely have some problems to compete with that. And some last words by the lemma of Seer. You can see that the solution will take, so the solution UH in the subspace is somehow optimal in the subspace. This norm here is the energy norm. That is equivalent to the norm of the original space, and you see that your true solution U and your approximated solution UH is bounded above by some constant and the norm of your true solution and all the test functions in the subspace. So optimality in the subspace. So now come to the case of stochastic coefficient. What we try to model is somehow uncertainty in the media. So when you consider the example presented of Darcy's law, so you consider some groundwater flow, then the information you have mainly is based on some samples. So you will not know how the ground looks in full generality, and you somehow have to interpolate between these samples. So there's uncertainty how to do this. There also can be, I don't know, some cracks in the media. There can be different types of medias, and you do not really know where the border is. Can be modeled with stochastic coefficients. This is a more or less new approach. So there's also a lot of discussion in the FEM community, and we'll see what comes out and what they come up with. So what we allow is basically that our coefficients are stochastic. So we introduce a probability space omega bar, and our coefficients depend on space and also on such a realization omega bar. The FEM approach to tackle this problem is simply to sample realizations of omega bar and somehow have a deterministic problem that solves this via FEM. And as you see, then the expectation of the FEM problem will be just given by some weighted mean. And we hope that with our approach we can compete with that. So FEM, in a deterministic case, we cannot beat, but for a given accuracy, you may have many samples here, so you have to repeat FEM capital N times. What is also is a problem is that there is a stochastic field introduced due to the uncertainty in the coefficients. This is just for completeness, so this problem arises if you deal with FEM or if you deal with our SDE-based approach. You somehow have to represent these coefficients in the field, so in field, and this is done via, for example, this can be done via Brownian expansion. This is some kind of stochastic Fourier expansion that I will not go into detail here. Okay, finally coming to our SDE approach. So we consider another probability space omega tilde. Omega tilde will be the driver of our many of our SDE. So our SDE, capital X, depends on the starting point, depends on time, depends on omega tilde, which drives the Brownian motion, and surely depends on omega bar, which is an uncertainty in the coefficients. The SDE just presented, we know that this admits a solution. Solution is given by the initial point and then the integral over the drift and the E2 integral over the diffusion, and we have some boundary, we know that this is bounded, and we also can state some kind of infinitesimal generator capital L of this solution, just given by that. And now we are going to compare the two approaches. For that reason, we define a product space. So these two independent probability spaces will go to this product space omega, and in capital omega there live these small omegas that just are omega tilde and omega bar pairs. And let us assume that, for simplicity, our solution to the problem is just given by that integral, so our SDE representation of this problem. So it is what we are doing here. We have u depending on the realization in the field, and in our SDE representation we just integrate out here the uncertainty over omega tilde, which is a driving force of our Brownian motion. Then what we know, so what is the good news, is that here the left-hand side, it is somehow a FEM solution, so the expectation over the field of u of x is equal to the expectation over field and over the Brownian motion of our SDE-based approach. The price we have to pay for that is that the left-hand side is the variance of the FEM approach, so we just have the variance over the field, and this is less or equal the variance over the field and over the Brownian motion. Why is this the case? I somehow skipped the dependence on omega and omega tilde, omega quer of x, so the dependence is somehow hidden here in the expectation and variance operators. This line here is some special case of a total variance formula, so the variance of f of x tau is given by the expectation over the field and the variance over the Brownian motions, plus the variance over the field and the expectation over the Brownian motion. Here the right-hand side, this is exactly our FEM variance, and the left part, which I denoted by epsilon, this is what is the extra term, and this is always bigger than 0. So that is some of the price we have to pay for our approach. Our approach in a little more detail. One problem of our approach is that our solution u of x is only given as a pointwise solution. So for each starting point of our SDE, we get one solution, and if we want to have a global solution, then we somehow have to calculate many solutions for many starting points. The idea to do so is to regress over starting points, and what we want also to do is an expansion jointly in space, so over the starting points and the stochastic field. So, as you remember, in the FEM approach, it was somehow separated. You sample the field, and for one realization, you're doing a FEM algorithm, and here we want to do this together. And the idea is to sample a starting point C that that depends on the field. And from such randomly sampled starting point, we want to sample one trajectory. And this one trajectory gives us one solution, which is no good solution. But if you do this many times and then do regression, we hope to come up with some good solution. Okay, here shortly, what is our plan for the regression? So this is what we want to compute. We want to compute the expectation over the field and over the Brownian motion. We evaluate this function u, evaluated at the SCE capital X starting at C and stopped at tau, and the evolution of this SDE depends on Brownian motion and the stochastic coefficient. And yeah, somehow this is our regression problem, and our solution then can be represented as these regression coefficients we get out of that and the basis functions. Where we want to apply this. So, as I told you, there's a price we have to pay when applying our SDE approach. We get some additional variance term. What one can hope for is that the numerical complexity of our approach is less than the FEM approach, so we somehow can push the variances down and may compete, but maybe that's a little bit too optimistic. Where we have application possibilities is in high-dimensional problems. Yeah, Monte Carlo is known that it is quite do quite well for high-dimensional problems, and what we also may look at is solution on subdomains. So, as I told you, the main strength of our approach is a point-wise solution. That's something we right now cannot really exploit. But for example, if you consider the wing of an airplane and do some stress testing, then you know that when the wing breaks, it is mainly in a small region. So what you are interested in is exactly that region. But with FEM, you have to model the whole wing. And so this may be some application area where we, with our approach, just model this subdomain. As we are only in an early stage of our project, there are many things we can think about. So right now it's a very easy, straightforward implementation with an Euler scheme. So we could think about different SDE approximation schemes. We can think about using quasi-Monte Carlo methods. We started with some easy adaptive discretization within the SDE simulation, but one can do much more, and also right now there's only some naive choice of basis functions, so one could make many things better in that part. Here, once again, the solution to our problem presented earlier. This time, it's the SDE-based solution. So there's not really no really difference can be seen, which is also stated here. So we have on the left-hand side the absolute error of the FEM approach and the SDE approach, and on the right-hand side the relative error. Here is not much to see because we have some problems in the corner, so the relative error explodes in the corner, so you do not see much within the domain. And that's it. Thank you for your attention.
Any question or remark, suggestion to
How do you perform optimization over
Good question.
It says it's like a quadratic analysis. No, it's just it reduces just the usual regression.
Yeah, just do regression and just some, as I said, naive basis functions.
And basis function, what kind of basis function do you use?
Simple.
At the moment, nothing yet.
Monomials of degree 4. So pictures produced with monomials of degree 4.
I mean, do you have any results about the complexity? So in the beginning you said that for the firm approach you have repeated n times and then you take the mean of that. And
So I mean, the firm solution you obtain is in seconds. But to get a real reference value for stochastic coefficients, they computed, I don't know, 3 hours.
But we are not yet at the stage of stochastic data. I mean, this is all deterministic data where it's clear that FEM is better.
But for deterministic data, there is a complete theory on complexity. Or even on subdomains. You have a huge domain, you have a subdomain, you have smoothness assumptions, you get the complexity rates. They're known. I can tell you reference. From Monte Carlo.
Okay, if no more questions, I think we thank the both speakers.